Hello community! Domain-specific tokens. Are you still downloading BERT models that have been downloaded millions of times? Are you still using the vocabulary that is more than 4 years old? Are you still having in your tokenizer more than 1,000 entries of unused? Or you have language symbols you're sure you're not gonna use in your English text? Are you limited by the BERT architecture to 12 attention head and 12 layers? Well, then it is time to build your own. Starting from our sentences, we learn a tokenizer on our text, build an optimized tensor representation, and design a BERT model with our number of layers and hidden dimensions to optimize our results. But at first, we have to start with our specific tokenizer for our text. So, and here we are. Now let's code. Now easy, what we do every day is we have our pre-trained transformer model. So we install our tokenizer from Hugging Face, and from tokenizer import our tokenizer, and then we simply have a pre-trained model that we download, a pre-trained BERT base uncased model. And you say, yes, I know this, because if you go to Hugging Face and you go to models, the first model that comes up here with 25 million downloads is BERT base uncased. And if you click this model, you see, yes, beautiful. You have the model description, you have the masked language model, and the next sentence prediction this model was trained on in the pre-training task. But the most important thing is if you look for files and versions, you see here, let's increase this maybe even a little bit. These are the files that you need, and you have a vocabulary, your tokenizer configuration, your tokenizer file. So this is what we need. So if we go now back here and we load now this BERT base uncased, I want that you understand that this model has already, as I showed you here, a vocabulary. This is 4 years old. And if you look at this vocabulary, you see here unused, 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 and then more than thousands unused. And then we have the vocabulary. So if we rush down here, you see these are then the words that are encoded in our vocabulary. But what if you have a very special text? This is why we do this. So beautiful. Now, if we have now our tokenizer pre-trained and you want to say, hello, y'all, how are you? And you want to see how this is encoded, this is easy. Yes, if we execute this also. Yes, one after the other, unbelievable. And you have your token IDs, and you take your token IDs and you decode it. You see, this is the text that you get back. Beautiful. Now, if I have now a text like quantum chromodynamic, I showed you already in my last video, it is easy because you see quantum chromodynamic is not in my vocabulary as a word. Of course not, since BERT is word piece oriented. So you see here quantum chromodynamic is here 1, 2, 3, 4, 5, 6 pieces. So the word quantum. And we have, with this special prefix, we have then 5 additional elements. So the system is building up quantum chromodynamic with its vocabulary. And since the classical BERT is trained on the book corpus and all of Wikipedia, you have a good chance that your word is able to be deconstructed in this way. Beautiful. Anything else? No, you know everything. Yes, we have sentences. And when we have sentences, we can do the same. Beautiful. We encode in batch. Beautiful. And then we say, okay, show me with the pad. You see here we have here our special token. Hello, how are you? With a separator token. And then we have a special token again for the set in seconds. And of course, you see here our smiling face here, our emoji. We get an unknown token back because this is not in the vocabulary. Now imagine instead here of the emoji, you have a chemical wording or a biochemical phrase of a chemical substance. Then we want to optimize here our vocabulary. Be great. Yeah, attention mask, of course, everything is here. So what we have to understand is there are more or less 4 tokenizer models that are currently available. And I would like that you focus only on 2. This is the Byte-pair Encoding and the classical word piece encoding of BERT. You see that I have here a very short description how this tokenization method functions. With Byte-pair encoding, you can say it starts here with single characters, and then it goes up and builds new token. And if you want, I have a specific video on Byte-pair encoded for all the details. And the nice thing is that with Byte-pair encoding, it is able to build words it has never seen before by using multiple sub-word tokens. Thus, we have a smaller vocabulary and we have less chances of having unknown tokens. And this is why I would recommend BPE for you. But we are here with BERT and we want to build SBERT. And let's go the classical route with sub-word tokenization that was used with Google, from Google to train BERT. You have here this famous prefix that shows you that the specific word is broken into sub-word pieces with the specific prefix. Also a specific video if you want to learn more about it. Great. So now we are here, build a tokenizer from scratch. Yes, finally, we have here now our text model and now we're going to build our tokenizer. Great. So here we start. We need at first our text, so all characters present in the training corpus. Then we identify the most common pair of tokens. We merge the new tokens. We have an avalanche of token building up. And then we finally end up with a vocabulary. Beautiful. Now, as you know, a tokenizer has 4 steps. The first, or let's have this a look here, is the normalization, the pre-tokenization, the specific model choice, the training of the tokenizer, and the post-processing of the tokenizer for special tokens we need when masking or training BERT, for example, on a masked language model. So here we go. First, we normalize our input text. Now, you know that there's this beautiful Unicode normalization that is classical. So we say from tokenizer, import our normalizer. And from the normalizer, we have NFD, or you can import NFC. And you can strip also the accent. If, as you think about French, you have this accent on your characters. You want to get rid of this. Just show you this. It's very easy. Download it. And then we apply it here on this text where we have a lot of special characters. And as you can see, if you apply the normalization to this string, I get a classical English string back. Beautiful. This is how to build a normalizer. Now, you have here this Unicode consortium. If you will hear about the form C or the form D or the form KC or KD, here is a little bit of information for you. But this is a standard normalization procedure for strings. The second is interesting. This is pre-tokenization. Pre-tokenization is the act of splitting a text into small objects that give us an upper bound to what your tokens will be at the end of training. So normally we split on a white space so we get words. So the tokenization machine knows, okay, we have words, these are our chunks, and on the words, I work my magic. Beautiful. This is it. Let's do this. Import white space. Yes. And then we say here, for example, hello, how are you? I'm fine, thank you is our sentence. And if I have now the pre-tokenization to this string, what happens? Exactly this. Each word and each question mark or each exclamation mark gets its own position, its own word boundary. Great. This is what we end up with. Output is a list of tuples, each tuple containing one word and its span in the original sentence. Because afterwards, I will show you, we need, of course, positional encoding. You can have pre-tokenizers that take care about special digit combinations. We can play around. There's a lot of possibilities. Now, as I told you, third step is now we choose a model. And I would recommend a Byte-pair Encoding model. So let's do this. We have here our tokenizer and we import the Byte-pair Encoding model of the tokenizer. And we say, okay, if we have the nomenclature for some unknown token, it should be UNK. This is the standard procedures. Nothing special. And then comes the beautiful point here that if we build up a tokenizer from scratch, the vocabulary size. Here we are. Normally, if you have BERT for mask language learning, then we have here a fixed, a classical size of our vocabulary is about 30,000 tokens in our vocabulary. Now, we build it up so we can say, hey, so I need to increase my vocabulary size 45,000. No problem. We are here, we can define it. Or you say, hey, it is so simple. I have just, 100,000 sentences. So I just need a vocabulary size of 15,000. You can fine tune now here your specific tokenizer. So let's do this. We go only with 15,000. This is just for demonstration. The minimum frequency when it should start if it has the token. So below an appearance of 5 times, it will not include in the vocabulary side. So let's go maybe with 4. And of course we say, hey, we have special tokens. This is the unknown token. This is the start token. This is the separation token. Then we have padding because we have to bring all the sentences to the same length. So we pad it. And then for the training of our BERT model, we need a mask. These are our special token that we want to have in our training, in our BPE trainer of our tokenizer. This is it. Great. Beautiful. So what we do, what is missing? Missing is just here that we say, okay, as a pre-tokenizer, we take the white space and then we simply download our very special training data set. Here we have, 100,000 sentences. You have 1 million sentences, whatever. Your domain specific text. This is it. Here we are. And then what we say, and this is why we do it. Beautiful. We have our domain-specific text. We have our normalizer. We have our pre-tokenizer. Yes, great. And now comes the moment that finally I can now apply my training of my tokenizer on my specific, 100,000 sentences, maybe biochemical formulation or pharmacological formulations or very complex law wording, whatever you have. Here go your files. Here go all your text files. And as I show you, our very specific trainer that is now applied on these data files. Trainer here, where's our trainer? Here our trainer was our BPE trainer with a specific vocabulary size, with a specific frequency and a specific special token mask. So great. And then we say, okay, go. And now the beauty happens that now we build up our very specific vocabulary, our very fine-tuned tokenizer. So this takes some time and I just have a feeling that I'm running here with no hardware acceleration. Of course not. So this will take some minutes here because we only have a CPU with 2 cores, but normally it should be done really fast. So I will be back with you in a second. As you can see, after 2 minutes and 38 seconds, it is done. And now we have our tokenizer. And of course, we want to save our tokenizer. And the command is, as you imagine, .save. And we store it in a JSON file. Now, if you have a look here, you're not going to believe it. Here you have your tokenizer wiki, your JSON file. Let's have a look at the content of this file. And as you see here, we have here our unknown token with the identity 0, our separation token with 1, separation 2, padding is 3, beautiful, beautiful, beautiful. We have the normalizer, NFD and strip accents. We have our pre-tokenizer, that is white space, and the post-processor. I have to show you in a second. We will do this. And then we have here our numerical association of a specific character, of a specific language sign with our numerical encoding. And we should be limited to 15,000. Where are we? Because I said, hey, 15,000. Let's go. And then whatever this is. So Edmond 14,999 is our last word piece that we encode. Great. So you might say, isn't this beautiful? And if we come back tomorrow and we want to load back up our tokenizer, well, we do just simple tokenizer.fromFile. You have the path of your JSON file and you just execute this. Let's do this. And you can call it whatever you like. I call it my own tokenizer from yesterday. And I have loaded my tokenizer from disk. Beautiful. Now, I would like to show you how this tokenizer now encodes my quantum chromodynamic and quantum field theory perturbation-based theory. So let's do this. Have a look at this. How is it separating? And you see here, our quantum chromodynamic is now separated in 1, 2, 3, 4, 5, and 6 pieces. And as you can see, perturbation theory is now, at first, theory is now one word. It is not separated. Perturbation is now 3 words. And you see, this is beautiful. Physics is 1 word. Theoretical is still 2 words. But you see, we optimized our vocabulary. We optimized our tools that we use to generate a tensor. This will be the input to our transformer architecture. Beautiful. And of course, yeah, you see here the numerical presentation of this. And as you notice, if whenever you see something like this, you say, hey, there's something missing. Our special token indexation is missing because normally you start with 101 or you have somewhere 1 or 2. And this is exactly why we have post-processing, for example, for BERT. So what we do, we say here, we have very special token. Let's do this. I have this token here and I have this token here. It already knows the numerical number. And then what I can do is I have a template processing. And this is beautiful because you can do here for single sentences. You have a start token, you have the sentence in BERT, and you have an end token. Or you have a pair of sentences. I told you that the pre-training of the BERT transformer architecture happened on 2 tasks, on the mask language and on the next sentence pair. So for next sentence pair, we have here a very special token at the beginning, sentence A, separator token, the sentence B, again a separator token, and the special tokens that we use are at least these 2 tokens. So beautiful, this is it. And if we now look at this, you can see now my quantum chromodynamic is still here and we have our special tokens, especially if we have, as I showed you here, 2 sentences. We have here the first sentence and here's the second sentence. And as you see, of course, our emoji is still an unknown token for the model because it has not been trained on this. So beautiful. You might say, great, so we built here our BPE tokenizer model. And in the next video, I will show you how to build our BERT tokenizer.